Hello, my name is Dr. Jean, dear future people. Now we are going to talk about two new topics. One is mathematics, or more precisely, mathematics as seen from the angle, from the viewpoint of Vitologia. Well, we have established that life is something variable, flexible, in constant flux. It is continuously changing. We have established that we have densities on the basis of our detection capability. These are perceived as events, objects, individual units that may appear and disappear, but that behind those densities there is our perception capability, our classification, our distinction capacity. And now, from this background, we are gonna look at mathematics and see that in mathematics something entirely different is happening. We have the idea that there are permanent things. There are permanent objects, permanent operations, permanent geometrical planes and dimensions, and there are permanent relationships between those things. We have measures and operations that are standard, that are true for every observer. And from the point of Vitologia, this idea of standard things, of objective things, will appear as an attempt for standardization. And behind every form of standardization, there is an attempt for communications, for better communication. So mathematics, from this point of view, is a language. It is based on coordinated thinking, using common patterns in human mind function and then further coordinating these common patterns. So similar to Vitologia, mathematics is a study of human mental mechanisms. But unlike Vitologia, mathematics is using abstract units, objects, operations, and reference frames that are coordinated using logic. But then even mathematics change. Mathematical thinking went from straight lines in straight space to the possibility of curved lines in curved space. So that's a change. That's a kind of development. And so the same way we have a set of axioms, statements that are self-explanatory, statements that do not need proof, statements that are so obvious that they are assumed to be true everywhere at all times. And then we have problems with axioms. In fact, we have problems with any system that is based on a set of axioms. We have problems with consistence, and we have problems with decidability, and therefore predictability. So mathematics and mathematical thinking does change. Even in mathematics, there is nothing really permanent and unchanged. So again, what remains is that mathematics is an exercise in consistency of thought. It is consistent because it is based upon common patterns in the human mind that are explored and then coordinated. So that there, from the point of Vitologia, there's no mathematics without thought. Thought is the primary substance of mathematics because distinct units, sets of similar, identical, or even dissimilar units are a result of mentation. These are mental products. These are mental tools. And all of these are linked to active mind function and mind organization. So if we establish distinct units, for example, numbers, if we then describe the properties of numbers, then we have to be capable of abstraction, of classification, of seeing things similar or identical in a particular way. All of these things are linked to active mind function and mind organization because classification, distinction, establishing sets and distinct units, standard units, these are all dependent on mentation. Units are dense objects with sharp contours, and they are perceived as separate things, independent things, permanent things in the human mind. But this is contingent in the locality in which they are found. So they have to be in a low impact field so that they can be standardized. And it takes a mind to see these things as distinct. It takes a mind to imagine that there is such a thing as a low impact field. So what do we exactly mean by a low impact field? Well, let's study this for a minute. So let's imagine two kinds of spaces. One is an imaginary void with zero density of matter, energy, or any kind of impact, any kind of influence. So in such a space, we can have imaginary straight lines that we call spatial dimensions. And then 3 dimensions are going to establish, the position of a point. Why? Because one point is equivalent to another point except those 3 dimensions. But this is only possible if we have a low impact field. In fact, an impact field of 0 density. Because the minute that there are influences affecting the properties of space, then one spatial point is going to be different from another spatial point, not only in terms of its position, but also because qualitatively that area of space is going to be very different from another area of space. So if you standardize space, you have to imagine a low impact space where there are no other influences and you only consider the spatial orientation or extension or position of a distinct object. So that's exactly what we think about mathematics in general. That you have a low number of variables with fixed relationships, and that mathematics describes a low number of variables with fixed relationships, with the slogan, no matter what, everything being equal, those relationships are going to stay true independent of time or other influences. So you have straight lines, you have empty space, you have simple and fixed rules, and these are the products of the human mind. We choose to view things this way because of ease of communication, because of standardization. Now, the human mind's resolution, human associations, human perspectives, and human assumptions are necessary. They are all necessary to see things this way. And to make this simple, let's take this to the extreme so that we have a high contrast reality so that we can easily see the issue at hand. So let's take, for example, the mathematical idea of infinity. Well, how do we define infinity in mathematics? Well, it is really defined as an endless iteration, unlimited iteration of something based on a mathematical operation or a mathematical rule. Like series of numbers, for example. And then we even use this symbol to denote mathematical infinity, as if infinity was a number. Well, it really is not a number, is it? It's really describing an endless iteration of something, an unlimited iteration of something. Well, this is what we call a simple infinity, a low-dimensional infinity, because it is based on one rule, on one operation. And so therefore this type of infinity has a large degree of homogeneity. Well, look around you right now and see if in real life you have homogeneity of this degree. And then think about what would be the definition of infinity in Vitologia and how that is different from the definition of, or the concept of infinity in mathematics. Low dimensional infinity or maybe high dimensional infinity. So mental exercise, language, a tool for coordination, a tool for better communication. Being all of these things, mathematics is excellent for didactic purposes. It is excellent for just simply communicating. It is very, very important for as a model, as a tool for modeling, especially in natural sciences. So we use quite often, even in everyday life, mathematical modeling. And so very specifically speaking, we can say that we use the idea of a function, a mathematical function, even in everyday life, not to mention natural sciences. So let's talk about functions. Functions describe how one variable is dependent on another variable or a set of variables. So when we think about functions, we really think about relationships, standard relationships between variables. And so in mathematics, functions always have domains. Domains for functions is something that is defined as the area in which that function makes sense. An area where that function is defined. And the range is, of course, the values that the function can take within the domain of the function. So in mathematics, there are no functions without domains, and there are no functions without range. Every function has a domain and range, even if the domain or the range are infinite, going from negative infinity to positive infinity. But they always have a domain and a range. For instance, even the simplest mathematical operation, that is division, has a definite domain. For instance, it excludes division by 0, Why? Because there is no adequate interpretation for dividing something by zero, so that division by zero is excluded from the domain of the operation of division. So, as in mathematics, functions have domains and range. Then in real life also, if we use mathematical functions for modeling, then this model will have to have a domain and a range. Every function used in real life will have to have a definite domain and a range. So we introduce something that is going to be very useful for us in the future, and that is the idea of truth value. That is, if we use a mathematical function as a model in real life or in the natural sciences, for example, then we have to establish the domain and the range of that function. And if we choose to use that function outside of its original domain, then we need to examine how relevant that function is going to be under different circumstances and conditions. That is, outside the original domain where that function was originally defined. So the truth value is going to be the measure of how relevant that function is going to be in an extended domain. And that takes us to the next question, and this is a very exciting one, and that is, how do we establish similarity in circumstances and conditions? So how many variables do we need to use to see if something is similar to something else? And what resolution do we have to have so that we establish what are differences that we see as important and what are differences that we can just simply, neglect, ignore? So then we come back to the idea of sensitivity. We come back to the idea of resolution and consideration of number of variables being consensus-based. And that leads us to the idea of similarity between observers, similarity between thinkers, and the similarity in the angle, in the perspective that they are using when they make even a simple observation. And that, of course, leads us to something very exciting called locality. Now, we are going to talk about locality so much that any definition that we can make at this point can be only a partial definition. And the partial definition we are offering here is from the point of view of observation. So locality from the point of view of observation is going to mean the zone of observation determined by the focus, by the capacity, by the resolution of the observer, as well as prevailing local conditions and circumstances. So, an example of this could be seeing something. This, of course, will mean that seeing something is dependent on a large number of things. For example, how good our eyesight is, and that may be relative to the degree of focus, the capacity of our eye, the state of the eye. For instance, there could be changes based on physiological conditions like You see something entirely differently from if your blood pressure is low or if you have an eye condition. You see something entirely different if your mind is very well rested, as opposed to if your mind is tired. If your body is tired, body conditions may influence eyesight. And then, of course, there are weather conditions, then there are objects that may be blocking your view. So you always have a local view. To extend that, in other words, if you want to go to the idea that I see something and then others can see that thing also, then you have to extend locality. And if you extend locality, then you always have to introduce assumptions. So if you go beyond the zone of observation, that is one specific observer under specific circumstances, then you are always assuming that other observers are similar to you and that the conditions of observations are also similar. So here is a man looking at something on a boat, and he's observing something on the sea. So the zone of observation is, as we said, dependent by the focus, the capacity of the observer, and that includes, of course, any instrument that the observer might use for the process of observation, as well as conditions. So again, you're going to have a local observation, and then you're going to assume that under similar conditions, other observers might see something similar, so that you have a standard view. A standard view such as what you have in mathematics. In other words, different observers observe the same thing under similar conditions, if those observers are similar. You take that to the extreme in mathematics. So we introduce something that sounds like an idea, a concept borrowed from mathematics, but we are going to use this in a different sense. So we are going to call linear extrapolation a kind of extension of observation that is relevant to what happens beyond the capacity or focus of the observer, based on the assumption that other observers are similar and that conditions can be fixed, standardized. So what we are doing in linear extrapolation is we are extending the domain of an observation, like extending the domain of a function. And then we are going to automatically, as a hidden assumption without any further thought, we are going to extend automatically the validity of our observations. Always assuming that same circumstances prevail for other observers and that the observers are reasonably similar. Now we need to introduce reference frame. And reference frame exists as a concept in the natural science physics. But our definition is going to be different because we look at reference frames from a different angle. So a reference frame is going to be a set of variables prevailing locally, which are going to be used to compare or interpret something against. So these reference frames are used for comparison. And these reference frames use local patterns of variables. So reference frames, therefore, are by definition local. For example, we can use as a reference frame a certain range of temperature, the strength of the wind, humidity, luminosity, etc., as is approximately what is prevalent in that locality in which the observation takes place. So now we have to introduce the idea of a pattern. A pattern is a set of variables observed as they appear together. So we have a pattern of a certain temperature with a certain strength of wind, with a certain degree of humidity and luminosity, all appearing simultaneously together. So here's a pattern. But let's give some examples for patterns. For example, certainly high blood pressure, diabetes mellitus, obesity, kidney disease, often comes together with lack of exercise or excessive intake of carbohydrates and animal proteins, so that they come as certain values of variables often coinciding, and that establishes a pattern. Or a pattern may be something like, when I tell him not to do this, he does this anyway. So this is a pattern of behavior. Or a pattern could be that the position of Earth and the Sun and average temperature in a certain region on the Earth seem to correspond, because they seem to appear together as very common. So if one changes in one way, then the other thing will change in a similar way, similar to what happens in a mathematical function. So for instance, here we can see that the position of the Earth and the rotation patterns of the Earth are going to establish a certain pattern or maybe a tendency for weather changes in a particular locality on the Earth. And so here we are going to introduce something even more interesting, and that is a matrix. Now, of course, this is going to be metaphor. Again, borrowed from mathematics, but we are going to use this slightly differently. So we are going to define as matrix a set of observable variables that create a pattern. And so, for example, here at A11 and A22, certain values seem to coincide very frequently, and that creates a pattern. So if we then fix most of the values and assume that most of the values in this matrix are going to be standard, are going to be unchanged, then we can establish functions between a low number of variables. For instance, this is what we do when we write an equation. So one thing depends on 1, 2, 3 other things, irrespective of everything else changing, because we are going to assume that everything else really remains the same. So we are only interested in one thing as it changes dependent on these 2 or 3 or 4 other things. Okay? So that we are going to introduce extensions, meaning that the equation will hold under such and such and such conditions. And then we assume if conditions are similar, then the equation will hold in all other reference frames and all other localities, because other variables are assumed to change very little or not at all. So for instance, we are going to say that the weather is influenced as a function of Earth's rotation and position relative to the sun. But here, we are going to assume that all other conditions such as volcanic activity, gas composition of the atmosphere, wind, etc. remain largely the same. If in a matrix a lot of variables change at the same time, even if the change may be very slow and very difficult to detect, and these changes might be even undetected depending on the resolution and focus of the observer, then the relationship between these variables may change. And that is why we have to keep all these other variables as standard, so that we can really focus on the dependence of one variable versus one or two or three other variables as a mathematical function. So for instance, when we say that the water boils at a certain temperature, we need to understand that this is dependent on keeping the air pressure constant, because if the air pressure changes, this boiling point is going to change. So we understand that standardization and fixation of certain variables are always necessary to keep a certain relationship true. So if we write even the simplest of mathematical equations, for example, A equals B times C, like in a multiplication, then we assume a low variability matrix. We assume that all other factors that might influence this relationship are going to be permanent and they are not going to change. In a high variability matrix, such relationships may not hold because there are changes in other variables that influence this relationship, so that the everything being equal, the intrinsic properties of variables and relationships will simply not be relevant anymore. It's not only A and B and C change, but their relationship may change depending on a number of factors that we might not even consider, or the changes of which we are not able to detect depending on our resolution. So that, let's assume for a minute a high variability matrix. In a high variability matrix, there is no reason to describe fixed relationships between a small number of variables, because we have other variables that may change in the background that we may not even notice, changing these relationships. So therefore, equations, any type of relationship described by equations, will look at approximations, keeping certain circumstances and conditions relatively stable. But if that is the case, then we do not have permanence and unconditional truth of certain relationships, and therefore we have no use for the concept of existence, which is based on all of these things, all of these standardizations and fixations and assumptions, hidden assumptions. So when we think about existence, we first of all need to assume that there are, or there can be defined, constant separate units with fixed properties that are largely unaffected by most variables in the matrix. But of course, if we have a high variability matrix, then there are no fixed properties because every property may be influenced by a large number of background things. And there is no constancy, there is no permanence, because every pattern is unique. Now, there are more common patterns, but the patterns are going to change constantly. And therefore, everything will be conditional to how other things change. This is how high variability matrix works. So existence, the idea, the concept of existence makes sense only in a low variability matrix when things are fixed. You have an infinite domain and a very limited range for certain things. And that you call existence. So if your detection is spotty, that means you consider only a low number of variables that are important, only the high contrast, easy to see variables, only the high contour densities, then you might interpret this as separate and independent. And then you have the idea of a unit that exists. But in a high variability matrix, this simply doesn't make sense. Because a number of things change, creating very complex patterns. And if patterns are complex, you have a high degree of heterogeneity, variability, so that relationships will also change between variables, depending on background variables that you are not necessarily looking at, you're not necessarily considering at a time. And that is why observations based on the number of factors that you are considering and the number of factors that you are ignoring, standardizing, fixing, is going to be dependent on the observer, on the mentation of observer, how he frames his observation. For example, let's take the example of a human person, a human individual. So you think that a human individual, a human person exists, meaning that it is a constant, separate, independent unit with some dependence of other things, but largely having intrinsic properties. Well, from the point of view of a high variability matrix, then all what you are seeing is relatively constant patterns specific to a given density. And because you're not considering the highly variable nature of the matrix, then you will see this as a relatively constant, relatively independent thing. And depending on your resolution, you are going to see high contours visibly separating one type of space from another type of space, one space where there is something dense enough for you to see. So extension gives rise to existence, but in such a way that existence is based on extension into virtual space of an observation, and it's mechanical extension into virtual space. So let's go back to our multiplication equation example. So A equals B times C is a relationship between variables. This makes sense only if A remains A with constant and fixed properties. And so is B and so is C. So these are imaginary, constant, and fixed units. A is, and B is, and C is. And then A depends only on B and C. Now, of course, how easily this is found to be irrelevant in certain instances becomes important, even notorious, if we think about a biological example. For example, the calcium-phosphorus product, where the calcium-phosphorus product is, of course, determined by the level of calcium in the blood and the level of phosphorus in the blood. But that product will mean something entirely different biologically, medically, if the phosphorus is high and the calcium is low versus if the calcium is high and the phosphorus is low. So yes, mathematically speaking, if you standardize everything, then A equals B times C. That is true, but it's going to mean different, something entirely different. You know, if you give meaning to B, if you give meaning to C, because the biological organism is such that the mathematical relationship will hold, but it's going to mean something different in a biological system. So, the existence of A, the existence of B and C, and their relationships assumes a low variability matrix. And that is going to constitute a virtual or imaginary space. In a high variability matrix, these relationships may not hold. If every variable has the potential to influence every other variable and the relationships between certain groups of variables. So if you think this through, then you are going to conclude that existence is a product of mechanical extension of local observation, assuming a standard local observer and a low variability matrix. So, in other words, you are going to fix conditions and circumstances, and you are going to project these fixed extensions and circumstances into the future. So again, you assume that observers are similar, and you assume that they are going to conceive things, detect things in a similar way. Well, let's see an example for this. So, depending on my eyesight, I may see that this picture here, it consists of different units. For instance, a unit, say here, is independent from the unit here, okay? So this is separate from this. But if my eyesight is very good, I may see very thin lines that connect this imaginary unit from this imaginary unit. And then I'm going to see this and this as connected. So now I'm not going to see two separate units, but I'm going to see one unit. Again, this depends on my eyesight and the concept based on my observation. So the contours are dependent relative to the observer. One may see differences that are important, and the other person may not see differences that are important. So is this one single unit, or is this a meshwork of separate units? This entirely depends on the eyesight of the observer and the concept of the observer. you know. Some might see a special connection between this and that, and the other might see that, these are totally separate without any connection at all. So, from this, we may conclude that the very idea of existence is a paradox. It assumes a standard observer, which means that we have all the known observers. We can project the known observers to possible observers, and then we standardize, we extend what possible observers may be like. So if we assume that there is such a thing as a standard observer, and we assume that a standard observer means something that is very similar to all possible observers. So, if we do that, if we standardize the observer, then the observer simply falls out of the equation. So only the object remains. And then we call that object existing, independent of the observer, which is absurd, but that's what people think. So existence is a paradox because it assumes separate and constant units that are separate and constant for every possible observer, for every possible thinker. Fixed properties that are fixed no matter what the pattern is, no matter what other variables might influence, or what their influence might be. So then we create a virtual infinity in which all possible influences are fixed, so that we have constant units with constant relationships. So that the concept of existence is a result of extension into virtual space, into a low variability matrix, even a zero variability matrix, which is constant, which is permanent, which is not dependent on a lot of factors. Now, this makes a lot of sense in terms of mathematical modeling, but it makes no sense whatever from the viewpoint of Vitologia. Because since the substance of Vitologia is real life, what we see in real life is that there are common patterns, that certain variables change or seem to change dependent on other variables. If one has a value of 5, the other one very often has a value of 6, making the rule x plus 1, or the function x plus 1. But because we see a very high variability matrix in real life, where many things can influence many things, therefore relationships of things, equations will also change if we are willing to consider a large number of potential factors influencing relationships. And therefore, in Vitologia, existence does not exist, or existence in itself makes no sense. It is not a useful tool. So in mathematics, you have a virtual artificial world where units are separate and absolute. They are constant and their relationships are fixed. Mathematics therefore looks from the angle of Vitologia as a very useful mental exercise. But what it describes is an artificial, virtual, and very, very human reality. And then, to make this point a little bit clearer, we are going to study the nature of infinity in our next video. But before that, let us summarize all of what we said. We were talking about mathematics, but not mathematics from the point of view of mathematics, but mathematics from the point of view of Vitologia. We said that mathematics operates with standard objects, standard relationships, suggesting that mathematics is really an exercise in communication that is made easier by standardization. We also said that in mathematics, a lot of factors, background factors, are fixed. In other words, they don't change. If they don't change, then we have clear relationship between a few number of variables. We also said that in real life, this is not what we see. In real life, we have a high variability matrix with patterns that are similar, depending on what you see as similar, depending on how many factors you are willing to consider, and what kind of change you consider as significant, but that these similarities are not absolute, and the potentiality of combinations of factors are infinite. So that when you fix most of influencing factors, you fix most of the variables, then you have equations, then you have standard relationships that only loosely you can observe in real life. You see? And these kind of relationships are going to be in constant flux, and they are going to be interpreted differently by different sentient beings and different observers and different thinkers. So what we see here is, although we regard mathematics as a very useful exercise in communication, in consistency, we are going to make a difference between what we see in everyday life, which is a high variability matrix with a lot of things changing at the same time, and with patterns not necessarily constant, but only similar, and similar from a certain angle, from a certain point of view. And therefore, from this point of view, we are going to see mathematics as describing a virtual space, a virtual world. And we are going to say that in this sense, reality is much larger than the world of mathematics. The potential of life, and therefore the potential of mind, is going to be much, much larger than its mathematical models. And with that, we are going to conclude. Goodbye for now.